Okay, we talked about Bode plots, and we're going to try to do a Bode plot by hand right now. And I have a step-by-step method. So let's say we're given this transfer function, and we need to do the Bode plot for it. Step one is to find this gain I call k sub 0. And all you do there is plug in 0 for all these s's, and you get 8. And to do that in dB, we take the log of 8 and multiply by 20. It's about 18 dB. So, okay, we have k sub 0. That's step one. Step two, I call filling in the Hoven table. I have not seen such a table in any textbook, but to me, it vastly simplifies this. You kind of like transfer numbers to this table, and then from the table, it's pretty easy to sketch your Bode plot. First, what are the breakpoints? Remember, when it looks like this, you're going to have a 4, 2, and a 5. Those are your breakpoints. And I'm going to say there's also, I call it a breakpoint at minus infinity to handle poles or zeros at the origin. And we want them in order. So it's going to be 2 and then square root of 5 and then 4. Unfortunately, in this example, they're awfully close together on a log scale. We'll talk about that in a minute. So those are our breakpoints. And in order, they are this: 2 square root of 5, 4. We usually need to calculate these damping ratios for the complex terms, these zetas. And you can calculate it, if this is A and this is B, A is 2, B is 5, you calculate it to 0.45. And we'll talk about when zeta is important a little bit later. When it's very big, not big, but this is probably a little bit too large to worry about. It won't affect our plot. We'll talk about this in other examples. But okay, we have our breakpoints. We put them in the table in this left column in order. What is n? That's like the power. And I'm going to say it's positive for terms in the numerator and negative for terms in the denominator. In this case, nothing's to any, they're all to the first power. So the real guys are going to be a step of 1, and the complex guy a step of 2. So in the order they come in, this guy at minus infinity, or the guy at the origin, he's in the denominator, so that's a minus 1. Next guy is a 2, he's in the denominator, that's also a minus 1. Square root of 5 in the denominator, but it's a complex term, so it's a minus 2. And then this term is in the numerator, it's a plus 1. Then I probably really should add another column right next to this, which is the cumulative end. You add these up going down. So it would be minus 1, minus 2, minus 4, minus 3. Then the gain is 20 times whatever that cumulative n is. And the phase is 90 degrees times whatever that cumulative n is. So minus 20, minus 40, minus 80, minus 60 corresponds to minus 1, minus 2, minus 4, right? This is minus 90 times, or this is 90 times minus 1. This is 90 times minus 2. This is minus 90 times minus 4. And this is 90 times minus 3. Right? The first breakpoint, this will always be in every table. This top breakpoint at minus infinity. N is the power of that breakpoint. What if it's a real term? 2 for complex. Multiplied by the repetition factor. This example doesn't have anything. They were all to the first power. It's negative for poles, plus for zeros. And let's see. If there were not a pole or zero at the origin, this end here would be 0. But because there was a pole at the origin, that was -1 in this case. And look at the cumulative thing. The cumulative end, that's what these guys are based on, the cumulative end going down. I call it step 2.5. I'm not going to get into this, but I spent probably a lot of my time doing and redoing Bode plots because I didn't do my scaling of the graph correctly. You know, you're just given blank graphs. You get to put on what the increments are. And you got to kind of know where you're going, what this problem is going to require, so you don't have to totally redo the thing again. And I'm not going to go over this, but if you actually have to do one, it's worth spending some time getting your graph scaled correctly. I'm just going to skip over that for now. So step 3 is those initial asymptotes. We have that K0. Well, let's see. First, let's say I labeled. Here's how I labeled the frequency. Here's 10 to the 0. That's a important point. And you usually want some space to the left of that. So anyway, here's the frequency scale. And here's the gain scale. And if you could see, the phase scale is kind of easy. The most it is -90, and it has to go down to -360. So you just need a scale that will contain that. So here's how I did that one. So here is 10 to the 0. Go up. And here is that K0 was 18 dB, right? I think we went through that. That was step 1, was calculating K0. So put a little point there. And this line has a slope of -20 dB per decade. You get that from the Hoven Table. So this guy is going down 20 dB for every order of 10 in the frequency. If you look at it, that's right. So it goes from about, well, let's pick a 0 here. -40 there. So the next 0 is about -20, or this is -18. That's going down 20 dB per decade. So that's step 1, just that first asymptote. And you want to go a little bit past that. Actually, you want to go past the next breakpoint. Where was the next breakpoint? The next breakpoint was at 2 in radians per second. And 2 in radians per second is this 2 here. This is just plain old 2 right here. This is 20. This is 200. Right here is 2. So that's the next breakpoint. This 2. You want that asymptote to at least go through that next breakpoint. Now, what's neat is you keep doing asymptotes. Each one starts at the next breakpoint. The gain asymptotes, you keep continuing to the right until you at least go through the next breakpoint. Phase asymptotes are flat, and you always extend on both top and bottom. You extend it through the next breakpoint. And when you're done with breakpoints, you just go to the end where you go off the charts. The trouble here is all our breakpoints are really close. 2, square root of 5, and 4 are just from here to there. We have 3 breakpoints just over that little gap in frequency. So it's kind of hard to see exactly what happens between breakpoints here, but you're going to end up this final slope once you're through that last breakpoint is, go back to the Hoven table. It's minus 60 dB per decade. Each little increment increases or decreases the slope. It doesn't just add or subtract dB. It increases the slope of that gain asymptote. On the phase, it just plain adds or subtracts phase. So what do we look like there? So there was our initial asymptote. We go through a few, but we know by this point, we're just going down 60 dB per decade. You can check that out if you look at this at your leisure. I think I had a mistake here. This point shouldn't be here. It's a flat line at minus 90 degrees up until we hit that first break point. Then it dropped another 90. Got to the next break point, which wasn't too much further. And it goes down, I think, another 180. Then it goes to that break point at 4. And we go back to, it was 7, right? Look at the Hoven table. Those were those phases. And they kick in at these breakpoints. So that's our asymptotes.